More amine chemistry coming right up. Okay, so in the previous video we talked about the Gabriel synthesis, which is one way of making primary amines. The workup is not too difficult, but you do have to deal with that additional byproduct, phthalic acid, in the separation. So, you know, not super difficult, but also not the most attractive thing. Now, luckily, we have other routes of creating primary amines. So, for instance, we can treat an alkyl halide, not with amine, but rather with something known as azide. So this thing right here is called sodium azide. That's 3 nitrogens. That entire segment is a molecule and it has a negative charge. And it's a pretty good nucleophile, so you can actually make alkyl azide molecules like the one shown here. And not only that, but once you make those molecules, you can treat them with lithium aluminum hydride to undergo full reduction to a primary amine. Now, as smooth a reaction as that looks, there's one major drawback of this reaction, and that is the fact that your alkyl azide compounds tend to be rather explosive. And if you're not careful how you handle them, or worse yet, if you try to fully remove the solvent while handling these azide compounds, you could end up with, an unwanted accident. Not that there's wanted accidents out there, but this will be absolutely not a good situation to be in either. So that's one major drawback. Organic azides a little bit more better behave, so those ones actually worked out pretty well. But yeah, that's the only thing to be, careful about, from the point of view of synthesis. But this is another way of making primary amines, So Gabriel synthesis is one way, azide reduction is another. And as far as the mechanism goes, you start by first undergoing that SN2 reaction. And one thing I want to highlight is that as far as doing mechanisms for the azide reduction, you better be drawing out the azide molecule as is. It's not okay to just say N3 with a random lone pair attacking things. Like you gotta show this thing. And when you do that and elucidate the Lewis structure, what you should notice is that pretty much all the nitrogens are doubly bound to each other. And that means that the central nitrogen is got a formal positive charge, whereas the external or terminal nitrogens have a negative charge, right? So altogether, azide is negatively charged. And that's why we have the sodium cation to counteract that negative overall charge of azide. So one of those external nitrogens attacks your electrophilic carbon, breaking the carbon halogen bond and then producing your azide molecule. Okay, so that's how we get to this thing here. Now, on a separate step, so this will be like a sequential reaction, right? You now introduce your reducing agent, your lithium aluminum hydride, right? And once again, when you do the mechanism involving the azide, you gotta spell out that azide functionality. Don't get lazy. Don't just write N3. That's just not good. It's improper, and aside from being a bad habit, it's just poor manners. And your mom would not want you to do that. So um, you have your aluminum hydride pretty much attacking the very nitrogen that's right now connected to the carbon chain. And the reason for that is because one, between all the nitrogens available, this one is neutral, so it doesn't have a negative charge. And you can make the argument, okay, but the one in the middle is the one that has the positive charge, so why not attack that? And the reason why is because you don't have proper resonance to give you something a little bit more feasible. Whereas if you attack this terminal nitrogen, what will happen is that the electrons will get kicked over to the middle nitrogen, and then that will take care of that initial positive charge that you have on it, right? The moment you have those electrons coming into the middle nitrogen is now neutral. Additionally, the nitrogen on the bottom is also neutral, right? So you have basically reduced the number of formal charges present in that azo compound. And right now it's monoanionic because we still have the terminal nitrogen with 2 lone pairs, right, rendering negatively charged. So what happens now is that you do one more event, This time around, if you look carefully enough, what you wouldn't realize is that the terminal nitrogen sure does have those two lone pairs, but the nitrogen on the left side has one lone pair. And technically speaking, if the terminal nitrogen brings in its electrons towards the central nitrogen, and we simply break the nitrogen-nitrogen bond, single bond um, from the left portion of the A side component, what we're left with is dinitrogen gas, and that molecule, the moment it's formed, it's gone. So this particular step is irreversible by all intents and purposes. You end up, of course, forming deprotonated amine, which is a strong base. So right about this point is when you quench the reaction. You introduce water, obviously not uh, all at once. You probably want to do this with cold temperatures. Probably instead of just regular water, you just add ice directly to this thing to quench it. But nevertheless, water molecule is acidic enough to protonate your amides right here. So this will produce lithium hydroxide as a byproduct, but now you have your neutral amine. And because the conditions are basic altogether, you're not having to make the ammonium derivative and deprotonate that, right? You stop at the amine and you're good to go. All right, so that's how this mechanism works out. It's relatively, nice and straightforward, even, with the Lewis structure of the A side component. But then again, you really need to draw it to be able to depict all the things that are happening right here. All right, now that aside, you do have the issue of the explosiveness of this alkyl A side compound. So there's another route that you could also employ. This one uses nitriles in particular. And the idea right here is that you could have any nitrile that you want, but it does have to be an organic nitrile. This reaction, I'm not aware of it working all that great with, um, hydrogen cyanide. And on top of that, hydrogen cyanide is is a very efficient poison, right? So you'll be asking for trouble if you went that way. Um, so this will have a consequence, specifically that aside from the fact that we're going to be able to make primary amines via this route, uh, you're pretty much gonna be constrained to having two carbons at the very least on your carbon chain for this amine, right? So one carbon, maybe not super efficient route of doing this, and maybe potentially dangerous and fatal, right? So, stick with acetonitrile or bigger nitriles to do this type of thing. Now, as far as how that works out, basically you just have lithium aluminum hydride attacking the carbon of the nitrile moiety, and then those as that set of pi bonds simply move over onto nitrogen, and they give you monoanionic um, imine in this case, iminite, I guess, if we want to be technical for the name. And then what happens is that this takes place one more time. Another equivalent of lithium aluminum hydride simply attacks that carbon, making dianionic or dideprotonated, amine. So this thing is like super basic, right? Like this is ready to go. So the moment you add water, and you will have to do this slowly, cold water, you might even have to cool this down, to lower temperatures just to keep it, from undergoing a runaway reaction. But in essence, what will happen during the quenching process is that yes, the one of the lone pairs of that strong base will attack water. The electrons will move over to then produce hydroxide. You have lithium hydroxide as a byproduct in this case. One of the lone pairs has been already protonated, so now you have one proton here. But then that is also basic enough that it will attack an additional water molecule, producing another equivalent of lithium hydroxide, and then yielding your primary amine. So that's how that works out. It's not too difficult of a process once you have the chemicals, mixed together and reacting with each other. All right, so that covers two additional ways of making primary amines. In the next video, I'm going to show you how you could generate primary, secondary, tertiary amines via the amide reduction route. So I'll catch you on that video. Bye bye.